Okay, on to the third talk. So Tobias is going to tell us about programmatic strategy synthesis, resolving non-determinism in probabilistic programs.
Yeah, thanks for the introduction. I will be presenting a joint work with my colleagues Kevin and Tom and my PhD advisor Joost-Pieter. And yeah, this work is on programmatic strategy synthesis, which comes down to resolving the non-determinism in probabilistic programs. To begin, I would like you to think of this simple gambling game. So suppose we have two coins, such as this 1 and 2 pound coin here. But these are not regular coins, but they are biased, they are tricked. So they come up heads with probability, say, Q for the 1 pound coin and P for the 2 pound coin. And now the game is as follows. We repeatedly select one of these two coins and flip it. And then if heads comes up, we get the number of pounces on the coin. And otherwise, if tail comes up, we immediately lose this game. Say we start with X pounds. And we win this game once we have at least collected N pounds. And the objective here is just to collect at least N pounds, not to maximize something like the expected number of pounds. Yes. So the task is to maximize the probability to win this game. And here's a simple program modeling that game. So initially, we have not yet seen tails. And then while we have not collected N pounds yet and not seen tails, then here we have a non-deterministic choice. Yeah, so this if true and then true again is like a non-deterministic choice. And here we see that with probability Q. This means that heads comes up for the 1 pound coin, we get 1 pound. Otherwise, we lose the game. And similar for the 2 pound coin. How should we play this game to maximize the probability of winning? So we will encode this objective as a post condition whose probability we would like to maximize. The optimal solution looks like that. So there's no need to understand this exactly why. And indeed, the objective of this work is to find these predicates systematically. The idea is that these predicates highlighted in red encode a strategy in the sense that as we play the game, we just step through this program, and when we have to just make choices consistent with these predicates. Note that this strategy is permissive in the sense that there's still some non-determinism left. For instance, if P is exactly equal to Q square, then this choice is enabled, but this choice is also enabled. So in general, our strategies are not more restrictive than they have to be. This is also a parametric strategy in the sense that this whole game is parameterized in the numbers P and Q and N, and this strategy works for all these parameters. Overall, this is going to be just a semi-automatic technique. In the presence of loops, we will rely on user-provided invariant annotations, which is also the case in classical program verification. Our technical approach relies on weakest preconditions. So this is a picture illustrating weakest preconditions for classical programs. And here I would like to think of the weakest precondition as a map sending initial states to truth values. So in general, a weakest precondition is a predicate over initial states. And here I would like to think of predicates as functions sending states to truth values. And now the weakest precondition of a program C with regards to postcondition phi is a function that is obtained as follows. For every initial state, we look at all the reachable terminal states. And then we evaluate the postcondition at these terminal states. And then the weakest precondition will be 1 if at least one good terminal state is reachable. So note that this is an angelic interpretation of non-deterministic choice, which is a bit different from the standard, which would be demonic. Here's a simple example. So here we have a program where, well, if y is smaller than, or at most z, then we can set x to 1. And if y is at least z, then we can set x to 2. So note that there's some non-determinism if y is exactly equal to z. And the weakest precondition of the post x equals 2 is that y is at least z. Because in this case, we can simply take the second branch and set x to 2. Now, these weakest preconditions can be generalized to probabilistic programs and are then called weakest pre-expectations. This is also already quite old. And now this map perspective comes in handy. What is this probabilistic weakest precondition or weakest pre-expectation? It's a map sending every initial state to the expected value of some random variable f evaluated in the reachable final states. And this expected value is taken with regards to the probability distribution induced by the probabilities that occur along these computation paths. So here, for instance, this state is reached with probability 1/2, and that state is reached with probability 1/2 times 0.8, and so on. Here's an example of a weakest pre-expectation. So suppose we are interested in the final expected value of x at termination. Well, then, when running this program, we effectively double x on expectation. Yeah, with probability 1/2, we multiply x by 4. With probability 1/2, we set x to 0. Overall, this just doubles the expected value of x. This can be further extended to probabilistic programs that also have some non-deterministic choices. So notice that now some choices are purely probabilistic and others are non-deterministic. Here we can still make a decision. And the weakest pre-expectation in that case can be defined as simply to take the supremum over all possible resolutions of the non-determinism, also called strategies. Some people like to call that schedulers or policies. Here's another example. It's basically my two previous examples put in sequence. So I'm claiming that if I'm again interested in the expected final value of x, then in this case, if the initial value of y is at least z, then I'm claiming that this is going to be 2. Otherwise, it's 0. This is because if this is satisfied initially, then I can take the second branch, and then this part of the program doubles the expectation of x. So what's very nice about these weakest pre-expectations is that they can be defined inductively on the structure of the program. This is fairly standard, so I will walk quickly over these rules. For the only atomic program, the assignment that we consider, the weakest pre-expectation can be obtained by, so if you assume that you have some expression available for f, then you would simply substitute x by its right-hand side in that expression. This is completely analogous to the classical case. For sequential composition, you see that we first evaluate the weakest pre-expectation of the right-hand side. That indicates that to compute the weakest pre-expectation of the overall program, we move through the program bottom up. We will see that in an example on the next slide. For the probabilistic choice, we simply recurse into the two branches. The most interesting case is this non-deterministic choice, where here we take the maximum weakest pre-expectation of the branches that are enabled in the current state. For the while loop, we have to consider a fixed point as usual. This is an example how to compute WP. It's the previous example, I just made some more space. As you can see, we go backwards through the program, and we just keep applying these rules. We can simplify a bit in the middle, and just keep applying the rules, simplify. So it turns out that the maximal expected value of x after termination of the program is 2 times the maximal of the initial values of y and z. How do these weakest pre-expectations help us to compute strategies? So let me take a few steps back. So previously I had this purely non-deterministic choice here. Now I would like to restrict it in order to derive a strategy. And actually this is a very simple idea, but it's sort of the main idea of our approach. Well, these two predicates highlighted here in red tell us that, well, if we take this branch, then at the end we get expected value 2 times y. Otherwise, we get expected value 2 times z. Now we're interested in maximizing the expected value. So, well, let's just take the first branch if that value is larger than what we get in the second branch. And analogous for the second branch. Of course, we can also simplify that again. We can, if we want, keep computing our weakest pre-expectation, but it turns out that this is just the same as before, and indeed this is not a coincidence, as we will see in a second. So we formalize this sort of refining guards as a program transformation that does not alter the structure of the program, but just refines the guards. So it looks as follows. Atomic programs are just never altered. For the sequential composition, we again sort of move backwards. So we apply our transformation to the right-hand side, and then to the left-hand side, but with a transformed post-expectation obtained by applying this WP computation. For probabilistic choice, we simply recurse into both branches. And now the most interesting case is this the most interesting case is the guarded choice construct, where here you can clearly see that we make the guards of the choices more restrictive. We add a conjunction, and this is basically what you saw on the previous example. We just compare the WP of the two respective branches. Okay, this is for loop-free programs only. For loops, we will see it in a second. What does this transformation mean formally? What does it give us? Well, if C is a loop-free program, then all determinizations of our transform program, what does that mean? Remember that in the transform program, we can still have some non-determinism, but now we can resolve that non-determinism arbitrarily. So we could do that, but we could also do that. So for all such determinizations, this determinized program yields maximal possible expected value. Moreover, the transform program can be computed effectively if you assume that we have fixed some effective syntax to represent these expectations, as has been done in previous works. For loops, we rely on probabilistic loop invariants. I think in the interest of time, I will be a bit quicker here. But basically, we have these rules for probabilistic loops that are reminiscent of the standard Hawk calculus. And in order to transform programs with loops, we assume that loops are annotated by some user-provided invariants. And then to transform the loop, we simply apply our transformation to the loop body, but we use the invariant to transform the loop body. Note that this does not really depend on F anymore. This dependency is reintroduced implicitly because when we encounter loops, we also have to generate some verification conditions to ensure that the annotations were actually suitable invariants. And we have a very similar theorem for the soundness of our transformation with loops. Okay, to summarize, we have seen how to derive strategies for optimizing expected values after termination of a probabilistic program with non-determinism. For loop-free programs, our approach can be mechanized completely, at least in principle. For programs with loops, we essentially showed that we can reduce strategy synthesis to invariant synthesis. In our paper, we also showed a connection to the MDP of to the theory of Markov decision processes, and we also considered rules for minimization and for upper bounds. One possible direction for future work is to consider also stochastic two-player games. This is all. Thank you very much.
Thank you for the very nice talk. Do we have questions?
Hi, thank you for the great talk. So you can imagine that a strategy for resolving the non-determinism might want to keep its own local variables in general in a program. Does that sort of come up in your setting as like synthesizing a loop invariant that needs to keep around extra variables, or where would that sort of strategy show up?
So our strategies basically use the same variables that are in the program. I guess you could sort of restrict that so that the strategy can only use a subset of these variables, but then it would become more difficult, I guess. Yes. A great question.
Hi, cool work. So do you have any optimality results? I suppose when you have a loop, there's not always an optimal strategy, but maybe some epsilon optimal or...
Yes, so you're right. In the case of maximizing expected rewards, this is also what this Markov decision process theory tells us. There's not always an optimal policy, but indeed this theory tells us under which condition there is one. Yeah, I don't recall the exact conditions now, but for instance, if you're not interested in maximizing but in minimizing, then we can show that there always exists an optimal strategy. So yeah, there are some insights in the paper. Thanks.
Other question?
Thanks, that was a really nice talk. So in the case where you have a program that with positive probability, or maybe even probability 1, does not halt, that doesn't affect, or those branches don't affect what you're trying to optimize, but is there anything that you can say still about what the weakest pre-expectation ends up telling you in that case?
So if the program does not terminate only with probability 0, then the weakest pre will always be simply 0, so there's not much that your strategy can do. If it terminates only with probability, say, 1/2, then our approach is still applicable. Yeah, thanks.
Maybe one more quick question? Yeah.
So it's very similar to my example where I didn't have a loop, where you saw that I basically computed these refining predicates syntactically. And yeah, this can be done in general. The complexity will be rather high, but it can be done.
Okay. Thank you very much.
Thank you.